So, in the last lecture we defined a decomposition subgroup of a prime in. So, we have a relative situation k over f, we take a prime below and see how it decomposes in the field above. You take a prime above called capital P and we define decomposition subgroup of capital P. We defined a map from the decomposition subgroup to Galois group of the residue fields and we proved that this map is surjective. Today we are going to study the kernel of this map. This is called inertia subgroup and we are going to prove properties of inertia subgroup. Okay, so recall we defined a group homomorphism G sub p to Galois group of k sub p over k sub small p and proved that this map is surjective. Okay. So, definition I sub p, this is okay, let me write it as I sub p. This is kernel of this map G sub p to Galois group of k p over k small p. This is called inertia subgroup of P. Okay. And also recall that the order of G sub p is E times F and the order of Galois group of K P over K P is F. And so, we get order of this group is order of G sub p divided by order of Galois group of K p over K small p. And so, this is E times F over F and so, this is E. Okay. So, is non-trivial if and only if P ramifies in K over F. Okay, remember that K over F is Galois and so the prime above ramifying can be stated in terms of the prime below because one prime ramifies if and only if any other prime above P ramifies. Okay. So, let me write down a theorem recording what we have proved and maybe one more claim. I sub p is a normal subgroup of G sub p of order E, and if you look at the quotient group is a cyclic group of order F. Okay. Furthermore, there is a different characterization of I sub p. So, these are all elements in G sub p such that okay, alpha is congruent to sigma alpha mod p for all alpha in OK. Yeah, okay. So, this is kind of clear, but I want to make a stronger statement. I want to say this, right. it is clear, I mean the fact that if I write G sub p here, then it is clear that this is true, because I p is the kernel of this map from G sub p to Galois group of K capital P over K small p, right. So, so the kernel will induce identity map on K sub capital P, which is exactly this statement, right. Okay. So, so this is not surprising. What is perhaps a bit surprising is that you can replace G sub p by p. So, I will just state, I will just say why this is true. Okay. So, so this last statement, this is clear if sigma belongs to G sub p. So, let sigma belong be not in G sub p, and I want to show that it is not in I p either, right. Okay. So, what I can do is I can take, so then sigma of p is not equal to p, right. So, take alpha, sorry not this, alpha which is in p but not in sigma p, right. These are two sets which are not equal. So, you can always you know and one is not contained in another either, because they are maximal ideals. So, there will be an element alpha which is in p but not in sigma p. Yeah, okay. Maybe I should work with inverses here, and that will make it better. Okay. So, if alpha is congruent to sigma alpha mod p, then alpha will belong to sigma alpha will belong to p, because alpha is in p, okay, and hence alpha belongs to sigma inverse p. This is a contradiction. Therefore, alpha is not congruent to sigma alpha mod p, and that is what we wanted to prove, that it is not in it's not in I p, right. It's yeah, it does not satisfy this property. Okay. All right. So, yeah. So, what have we done? We have, yeah, let me draw a diagram again. So, there is this, and then there is F, this whole group is G, right. Then there is K G P, this Galois group is G sub P, and then there is K sub I P, and this Galois group is I sub P. This Galois group is isomorphic to Galois group of K P over K P. Oh, in the previous one I forgot to say why it is cyclic. So, G P mod I P, this is isomorphic to Galois group of K P over K small p, and this is cyclic, because it is a Galois group of finite fields, and Galois group of finite fields is always cyclic. All right. So, so this is what the situation is. So, here what we are starting to do is the following. We want to understand the big extension K over F, but we are going to break up the study of such a big extension into these smaller pieces. We are going to study the decomposition group first, but to study the decomposition group, we will study it in two separate parts. We will study the inertia subgroup, and then we will study the quotient of decomposition subgroup by inertia subgroup. And we know that the quotient of decomposition subgroup by inertia subgroup is a Galois group of a finite field. So, that is it is cyclic, and we can answer many questions about it. Okay. So, that is kind of easy. So, the part that remains difficult if you want to study decomposition subgroup is the inertia subgroup, right. Inertia subgroup Well, at the moment it is kind of mysterious for us what it is, we do not know a lot about it. So, here we are going to take the first step to understand it, and there is actually sort of lots of steps that one can take. You can decompose your inertia subgroups into smaller pieces and try to study each of those pieces separately. And this is a very fruitful technique in algebra. This is kind of what is called studying graded pieces in some sense, or studying a filtration more accurately. So, we are going to study the first step of this filtration, but we are not going to look at the whole filtration as such. Okay. All right. So, what we can do is the following. So, I am going to define what is called wild inertia. So, this is first step of the filtration. So, you have inertia subgroup, and even within this there is something called wild inertia subgroup, which is kind of a harder piece, and then the quotient is what is called tame inertia. So, as the name suggests, it is kind of more manageable, it is tame. All right. So, how do we define wild inertia? So, what I am going to do is I am going to take alpha in OK such that P is the exact power dividing the ideal generated by alpha. So, this means that i.e. P divides alpha, but P square does not divide alpha. Another way of writing this is that alpha belongs to P, but not to P square. So, there are these three different ways of stating the same thing, and this is the two different ways of saying the same thing, and this is the notation for it, P with two vertical lines. So, instead of just one for divisibility. Okay. And then I am going to take P sub small p to be all the elements sigma in I sub p, such that sigma of alpha is congruent to alpha modulo p squared. Okay. So, rather than going mod p, I am going to go mod p square. Now, the first thing we need to show is that this p sub p, the definition seems to depend on the choice of alpha. So, here is a lemma, P sub p is independent of the choice of alpha. Okay. All right. So, so then we do not need to put it in the notation, and it also will tell you that it is a group. Hence, P sub p is a subgroup of I sub p. Try to prove it without proving the independence. If you take two elements in P sub p, their product should also have the same property, and yeah, it's kind of difficult to prove it without proving the fact that it's independent of the choice of alpha. Okay. So, how do I do this? Well, recall what we had proven first. So, recall that we had proved, maybe I am sort of doing a harder proof than is necessary, but anyway, here is a proof that I can think of right now. So, recall that we had proved that OK modulo p to p modulo p square, where x goes to alpha x, is an isomorphism. of groups, if you like, of additive groups. Okay, so so any alpha prime in P minus P square can be written as alpha prime equals to x times alpha plus some error term which I will call epsilon, right. So, for some x in OK and epsilon in P square. So, what I am going to do is I am going to write sigma alpha prime minus alpha prime, and if I write this I get sigma x alpha plus epsilon minus x alpha plus epsilon, sorry, yeah. So, this I can rewrite as sigma x alpha minus x alpha plus sigma epsilon minus epsilon. So, this thing is in P square, sigma epsilon minus epsilon. So, I can ignore that, but anyway let me, I will just carry it around anyway. So, this I can write as sigma x times sigma alpha minus sigma x times alpha plus sigma x times alpha minus x alpha yeah, let us see if this gives me the right thing, otherwise I will change it. So, this is okay, sigma x sigma alpha minus alpha plus x, sorry not plus, yeah, let me write it as minus alpha, oops, yeah, okay. So, this does not seem to give me what I want. X times sigma alpha plus x times sigma alpha sigma alpha sigma x minus, yeah, okay, I think yeah, even the first one was fine, but okay, let us work with what I have. Okay. So, in this, yeah, so the first quantity, this thing is in P square, because sigma alpha is in P square and this, right. So, sigma alpha belongs to P and, yeah, I said P square, but what I mean is this is in P and this is in P. This quantity is in P square as epsilon is in P square. Okay, so, yeah, so this means that x sigma alpha minus alpha is in P square if and only if sigma alpha prime minus alpha prime is in P square. Okay. And therefore, we get what we want, right. We get the lemma about independence of P. All right. So, so that is good, and hence we get that P sub script P is an is a subgroup. So, this is called the wild inertia subgroup, and here is a theorem about it that tells you why it is called wild inertia and why it is its quotient is called tame inertia. Okay. So, the theorem says that P sub P is a normal subgroup of I sub P. P sub P is the unique p-Sylow subgroup of I sub P, and I have to tell you what this P is. So, capital P intersected with Z is P times Z. So, that is the prime number P, right, because this P is the prime number P, it is not a typo here. And I sub P, so if it is a normal subgroup, I can take the quotient group. And what is this quotient group? This is cyclic of order dividing norm of P minus 1. Okay. So, norm of P will be a power of this prime number P, and so when I am taking norm of P minus 1, this is something co-prime to P, right, and which is what is expected. If you are quotienting out by p-Sylow subgroup, the quotient should not have order divisible by P, of course, and it does not, and in fact it is a cyclic subgroup, and we understand something about its order also. Alright, so that is amazing. This theorem tells you that this inertia subgroup, which is kind of difficult to study, you can break it up into two parts, which is wild inertia and it is a P group, and then the quotient, which is again a cyclic group, and we know something about its order. So, here is a proof. Okay. So, first claim is that P sub P is a P group. I mean, if it is a p-Sylow subgroup, it better have order which is the power of P, prime number P. Okay. So, so what we need to show is that any element of this wild inertia subgroup has order which is a power of P. So, what you do is you take P sub P, sorry, sigma in this, but not the identity element. So, there exists alpha in okay, let me take alpha in P such that sigma alpha is not equal to alpha, right. We just know that their difference has order divisible by P square, but of course they will not be equal, right. If sigma fixes P point wise for each element of P, then sigma gives me then sigma has to be an identity element, right. And so, what we can do is we can but we know that sigma of alpha minus alpha this thing is divisible by P square. So, what we can do is we can write it as follows. So, this is very similar to the idea that was used here, and so I am not going to recall it again. So, if you like, you can take that as an exercise. So, this is right. So, this is equal to some x times alpha to the m modulo p to the m plus 1, okay, for x which is not in P, right. Okay, and m bigger than 1. Okay. So, we can, okay, so maybe it is better to write it as follows. So, this should be congruence. So, if I keep applying this again and again, I get sigma to the r applied to alpha is congruent to alpha plus r x alpha to the m modulo p to the m plus 1. Okay. Right. And if p does not divide r, then sigma to the r alpha cannot be equal to cannot be congruent to alpha modulo p to the m plus 1, right, because alpha to the m is not in p to the m plus 1 and r times x is also not in p. Okay, so this means that order of sigma has to be divisible by p. This does not quite prove that its order is a power of p, but you can apply same argument to any power of sigma. Hence, order of sigma is a power of p. Okay, therefore, therefore, p sub p is a p group. Okay. And now we just need to show that it's we need to show two things. We need to show that it's normal and that its quotient I sub p modulo p sub p is cyclic of that particular order. So, what I am going to do is I am going to define a map from I sub p into OK modulo p cross. So, this is of course k sub p cross, and what is this map? Well, you fix such an alpha as before and you send sigma to sigma alpha by alpha. Okay. So, sigma alpha by alpha, its image in here does not depend on the choice of alpha, as long as you have this. So, this is a okay. So, the claim about this is that this is a well defined homomorphism with kernel p sub p. Okay. All right. So, it is clear, this claim is clear because as I said, it is independent of alpha, we saw that before, and then its kernel is by definition p sub p. So, hence p sub p is normal and I p modulo p sub p has order. So, this is a subgroup of k p cross, and what is the order of k p cross? This is by definition norm of p minus 1, right. So, hence order of I p modulo p sub p divides norm of p minus 1, and p sub p is the unique p-Sylow subgroup of I sub p. This comes from the theory of p-Sylow subgroups, right. If a p-Sylow subgroup is normal, then it is the unique p-Sylow subgroup. Okay, so we have now broken up the study of this inertia subgroup into two parts, wild inertia and then the quotient which is called tame inertia, right. And as I said, one can define further subgroups of this wild inertia. These are called higher ramification subgroups, and it is a very fruitful way of studying these inertia subgroups, but we are not going to pursue that in this course, although it is an important part, and at some future point you may want to learn it. But that is the way to study the decomposition subgroup, right. So, let me recall what we did. We have our Galois group which we want to study of the Galois group of this number field K over F. Our strategy is going to be we study it using decomposition subgroups for various primes, and so right now we are just concentrating on one prime at a time. So, we want to study the decomposition subgroup. We first broke it up into two parts, inertia subgroup and then the quotient which is cyclic, and then for inertia subgroup we looked at the wild inertia and then the quotient which is cyclic. Okay. So, that is what we are going to that is where we are going to stop about study of decomposition subgroups. In the next lecture we are going to define some maps from ideals into Galois groups, and this forms a very important part of algebraic number theory. These are called Artin reciprocity maps, and that is what leads to class field theory. We are not going to pursue class field theory in this course, but this course forms a basis of studying class field theory. So, that is what we are going to do next time. Thank you.